This video, I'm going to show you how to write electronic configurations. So there are two basic ways that you can write the electronic configurations. You can write it using the notation that I mentioned briefly at the end of last video, or you could show it with arrows to represent electrons. And I'm going to show you both methods in this video. And I'm also going to tell you a few important rules. You'll want to remember the names of these rules and what they tell you about as well. So to start, there are three rules when filling out electronic configurations. The first of these is the Aufbau principle. So the Aufbau principle says that you need to start filling in electrons from the lowest energy orbitals and it basically work your way up from there. So what does that mean? Well, if we look back at the periodic table, basically the higher up on the periodic table, so the lower the atomic number, the lower energy those electrons are. So that just means you have to start up here in the 1s and work your way down when filling in electrons. And again, as we get through the video, it'll make a little more sense what that means. The second important principle that you need to know is called the Pauli exclusion principle. And this says that no two electrons in an atom can have the same four quantum numbers. So hopefully this is pretty obvious for you to see why. But remember, when I was talking about the quantum numbers, I mentioned that quantum numbers can effectively be thought of as coordinates to tell you where in an atom an electron is located. So if two electrons had the exact same four quantum numbers, what that would be implying is that they're occupying the exact same region in space. And obviously, two different things of matter cannot occupy the same exact region in space. So at least one quantum number has to be different for every set of electrons, in an atom. And the last principle you need to know is called Hund's rule. Now, this one won't quite make as much sense until I get to the arrow notation that I alluded to earlier. But what Hund's rule says is that you have to fill in degenerate orbitals, and what degenerate means is they're orbitals of the same energy. So these are orbitals with the same energy. You fill them in one electron at a time, with the same spin, until all are occupied. And again, that will make a bit more sense in a few minutes. So, I'm going to use sulfur as an example, since I used it as an example in the last video a few times. So if we need to write the electron configuration for sulfur, well, basically we can just start with the notation that I mentioned last time and count along the periodic table. So we just have to start from hydrogen. So 1, 2. So hydrogen and helium, remember, they're both in the first energy level. and they're both part of the s block. So that is your 1s, and both of them are occupied. We just keep until we get to the element that we are looking for. We just assume every one of these is occupied. Right? It's not really an assumption, but so they're both occupied. So there are 2 electrons there. After that, the third element is lithium. And lithium, you can see, is in the 2s. So it's in the second energy level. So that's where the 2s comes from. And it's in the s block. So now, after the 1s comes the 2s. And lithium and beryllium, well, we still haven't gotten to sulfur, so they're both occupied. So 2s2. After the 2s, well, we're still in the second row, but now we're in the p block. So now, we've got 2p. And we keep going 1, 2, 3, 4, 5, 6. We haven't gotten to sulfur yet. So 2p6, because they're all occupied. All of the electrons are there. After that, so that takes us to neon. Then we have to keep going. The next element is in the s block, and it's in the third row. So now we've got 3s. Both of them are needed. After magnesium, now we get into the third row in the p block. So it's 3p. Now we keep counting all the way to whatever element we're looking for. In this case, sulfur. So 1, 2, 3, 4. So the p block, as I've mentioned before, can have up to 6 electrons. But we only need, in the 3p subshell, we only need 4 electrons in order to get to sulfur. So it's 3p4. And that's it. That is our electron configuration for sulfur. Now another way we can write this is with, as I mentioned, the arrow notation. So we can use lines. Sometimes you'll see boxes. I prefer to use lines. Either one is fine. So a line represents an orbital. So if you remember, in a couple videos ago, I talked about how, actually, let me show this one. In an S subshell, you can only have 1 orbital, so you only need 1 line. In a P subshell, you can have 3 orbitals. Now, any orbitals that are in the same subshell as each other, those are degenerate to each other, which means that all 3 of these have the same exact energy. All 5 of these in a D subshell have the same energy, and all 7 of these in an F subshell have the same energy. Right? So, this is your 1s orbital. Now we go to the 2s. You want to leave a space in between. Now, the P subshell, as I just said, has 3 orbitals. They're all degenerate. So if they're degenerate, you want to put them in their own group, but kind of keep them together. So that is your 2p set of orbitals. Then we go to the 3s. And then lastly, the 3p. Now, and again, each one of these lines represents one of the m sub l value orbitals. So now we have to put in the electrons. Remember, there are 2 electrons per orbital, one with a positive spin, one with a negative spin. So the way we represent that is by just showing 1 arrow pointing up and 1 arrow pointing down. 1 up, 1 down. Because, we have 2 electrons in the 1s, 2 in the 2s. We have 6 in the 2p. We have 2 in the 3s. Now we only have 4 in the 3p. So this is where hopefully Hund's rule makes a little more sense. So Hund's rule, when you have degenerate orbitals, you have to fill them in with the same so 1 electron at a time with the same energy. So for instance, let's say I'd stopped at phosphorus, and there were only 3 electrons in the 3p subshell. I would have to have 1, 2, 3. You would have to put each one in its own orbital, and they all have to have the same spin. It doesn't matter if you have them all spin up or spin down. That's irrelevant. Just as long as whichever one you choose, up or down, they all have to be the same. Now, but I still need 1 more electron here for a sulfur, right? So now, once I have gotten to the end, and all of the degenerate orbitals have 1 electron in them, now I can go back to the first orbital in that group and keep filling in until I get to the rest of my electrons, which in this case is just 1 more. So this is the arrow notation for the electronic configuration of sulfur.